Good morning, everybody. Welcome to my presentation. Subject Naval. The members name, and zero. Let's go into the content. First, main objective, then preliminary thinking, the final thinking, preliminary design of the project, after the conclusion. The main objective is very simple. How to make a ship more shock resistant so that it can withstand more shock. Our preliminary thinking was a little bit funny. We thought that if you can generate a negative wave from the ship, then it can withstand the shock wave, but it really is not possible. Then our final thinking was like that. Actually, the main catchword of that final thinking is that air acts as an insulator that cannot conduct the shock wave. So we want to make a bubble barrier around the ship, and those bubbles will contain air so that it can withstand and it can act as a barrier from the shock wave. And this is the primary design. Around the screen, we want to install some types of devices which will create bubble, and this bubble can reflect the shock waves. And at present, there are some types of bubble generation mechanisms. Here are the pictures of those bubble generation mechanisms, and these can create bubbles. That's the main portion of the presentation.
Any question?
I don't really have anything, but because in Singapore our ships are pretty small compared to the general ships. We don't need that big ships compared to a Korean destroyer that I've been on is smaller by at least twice. Our biggest ship is probably as big as a petrol ship in Korea, because our biggest ship is about 141 meters, which is pretty small, and that is our biggest ship. Our smaller ship is like 20 meters. So Singapore Navy is really more specialized on the small ship application. So
What's the speed?
Maximum speed, we have a cap is about, for the Corvette, missile Corvettes is about 20 knots. That's our limit cap. I cannot tell you if we remove the limit cap how much it will be.
So that's really a high-speed craft.
Yeah, but our minesweeper goes slower. It's about 8 to 10 knots, because we don't want to create some acoustic noise that might detonate the mines. And patrol crafts is probably 10 to 12 knots.
Is it is monohull or
monohull? Because we deal with thin hull trucks, thin hull ships, which is why with that we got in mind when we attended the short presentation by Mr. Shin's research student, Mr. Dongwan Chen. Yeah. I got added from there that the speed of the ship may reduce the shock to the ship. So what I want to research is what is the optimum speed that the ship can go so that it can sustain minimum damage from an explosion. Yeah. So what I intend to do is use the commercial software LS Dyna to simulate the moving ship according to my military ship's geometry and see how the speed affects the stress to the ship, and then find an optimum ship for the operation. So that's about it.
Can you get the geometry of the Singapore, the Navy's high-speed craft?
I can get one for the corvette, or the decommissioned gunboats.
Okay, that's a good project.
Hi there, I'm Chorong-Kim, my name is Joan. So, I saw so many their ideas for this project, so I wrote some interesting something for you. It's simply say the interaction of our motion. So, I give you some example for your understanding. So, there is the rectangle, and I put there one side, the big size of tanky, and then I put on the side the small size tanky. As you know, this big size of tanky makes the big bubble, and it has the high pressure, and then the small size has the low pressure. So we are wondering this motion, how to move this bubble with each other. So our community is studying like these bubble motions. Yeah.
Okay, hello. The subject of our project plan is the vibration analysis of ship equipment by shock. Our crew members, Renok Shin and our content of plan is as follows. I introduce our background, our plan. Surface ship or submarine can be exposed to underwater exposure. When it is affected by explosion shock, survival of equipment in the ship is a very important issue. Previous lesson, we saw the movie clip U571 and another movie clip. So we thought the equipment, the vibration on the equipment is very important problem. So the vibration level of equipment under the shock environment must be appropriate in its operating conditions. So our goal is to reduce the motion of equipment subjected by shock. And first of all, we will show the shock influences for the effect of explosives, and then we calculate motions for 1 degree of freedom system of equipment, where our assumption is that the ship structure is rigid. Just only we want to show the motion of the equipment, and then if possible we will show a vibration observing method for design, pragmatic design also vibration problem. So we will work in the future using MATLAB software and our knowledge from our next course and vibration courses. We will program for the calculation of the shock effects of the ship. And at any point from an explosive, maybe this is Nalo's work, and I will model the equipment as 1 degree of freedom. After I will set up a total program to connect to a code, so we will analyze the result of motion of the equipment, which includes the pre-process and post-process. And then we will find out the suggestion on observing method from the results. Yes, sir.
As I might mention to you, nowadays any conference you attend, time limit is 20 minutes, most over 90%, unless you are invited as an invited speaker. Then you have like 40 minutes max. And another 10 minutes discussion session. And most important in presentation is how to organize talk. I want you to practice through this project how to organize. How can I deliver the things I want to deliver in usually about 15 minutes. 15 minutes of 5 minutes discussion. Usually we end up having around 17 minutes talk and about 2 minutes in discussions. The same thing in our department. At the end of the last quarter before you graduate, then you will give a presentation. It's going to happen the same thing. 17 minutes presentation, 2 minutes discussion. So organize your presentation, organize your thought, then practice it. And that's a role for success. Okay, we started last Wednesday, generalized tailor plate. We did about 1/3 of it. And the generalized tailor plate is almost identical to the initial tailor plate theory, which is the beginning of the fluid structure interaction phenomenon. So here in this case, quickly, I'm going to go down to the point where I start here. So here in this case, you see one side, left side is air, and right hand side is water. And it has an infinite plate. Infinite plate is very thin plate. Okay? So we are dealing with per unit area, mass per unit area. Then over here, K is like a stiffness for the plate, and we're gonna deal with the stiffness per unit area, right? Otherwise, it's infinite mass, infinite stiffness. So B is like a damper. So we use in vibration theory, usually notation we use is a C, but to make a difference from the C here, so I use a B for it. And air and water. This is the wetted side, this is inside the ship. And here, this can be the hull. Very simplified situations. If the air side is water, then that's the flooded area. There's always in the ship design and also submarine design, there's areas, both sides flood. Okay? So, for the common sense, when an explosion occurs some distance away, then shock wave will hit it. One case is air, another case is water. So, which case will give more damage to the plate or hull? You follow me? Which case? Case 1, water, air. Case 2, water, water. Which case more damage could occur? Obvious, isn't it? A or B? Okay. Case 1, water, air. Case 2, water, water. As some said, it's case 1. You feel as a common, I'm asking common sense. Is case 1 air, water, or water, water? So, 50% chance of winning. I mentioned to you, the water is like an anchor, low sea. Water, one side, one low sea. Water, another side, both sides, another temperature. So two low sea. In the equations of motion, visualize mx double dot plus cx, right? Plus cx dot plus kx, right? C is rho c, right? Just visualize it. Rho c, one rho c, one side water is one rho c. It is the other side is water, two rho c. So who is going to prove it? After I finish this, you will do that as a weekend mini project. It's not even a project, it's a homework. After you learn this generalized play theory, very clear. Then equations of, remember this, positive x direction is left to right. So here, the incident shock wave is right to left. Okay, that has good meaning, as you saw down here. Now we cover all of them here. So you remember this? I said look at chapter 2. Then you will see forward traveling wave and backward traveling wave. That's where we have to do attention. Anyway, then boundary condition is what we have. We have done this last Wednesday, and boundary condition means you right at the face of the plate, which is interface between the water and the plate. And this equation, that's what we have done in chapter 5.1. So mu over there, u, which is a function of xt, is equal to minus del p. Whole thing is a vector. Whole thing is a vector, del over del p, which is a function of xt I plus del p del yj plus del p over del Z. K. I should say this is in general x, y, and z. And this is all equal to 0 because it's one directional motion, right? We set s. So this becomes simply del V over del S. So this is and another equation, this is del V over del X. We know it's in x direction. If you simply say, dropping the vector notation, U is equal to del V over del X. This is enormous. And we derive this relationship, right? So we know that P xt is equal to rho naught P dot, which is equal to rho naught del P over del T, which is like then her equation set is wave equation form is equal to C not square. So this is a basic set of equations to solve this precise problem for extended generalized plane chart. This is about it. 1, 2, 3, 6. That's what we did last Wednesday evening. Initial condition that T is equal to 0. Boundary pressure right at the base of the plate at x is equal to 0. P is equal to Pi plus Ts. Pi, do you know Pi? Yes, you know. What about the Ts? That's a scattered wave. Scattered wave is the wave which reflects from the moving part. So that's a scattered wave. Remember, that's unknown. That's what we have to solve for. So scattered wave has two parts. What part does it have? One part is reflection wave from the rigid surface. Two parts, one part. What's the second part? The second part is pressure absorbed by the plate due to the motion of the plate, which is rho C, U part. Remember? Because U is, when I say rho C, U is the motion of the plate. So two parts, that's what we learn. In solution phase, we look at the wave of propagation solution. This is before solving for vibration. So we will look into wave solution, traveling wave solution. Then you assume, of course, P is equal to Pi plus Ps. One is incident, the other one is suspect. This is revealed in this. Now, I did up to next page. This is Pi is incident at first. here is incident wave velocity. Ps is the scattering wave velocity potential. P is, regardless, P is the velocity potential. For S, for scattering, I for incident. Then here, in the defining process, PIXT is equal to, I use the function psi L. Why I put the L here? L is to the left, because the shock wave is moving negative x direction, so to clarify to myself, I put the L, psi L, to the left. So then, this is T, this notation, this is important. That is true. This, chapter 2.2, forward traveling and backward traveling. This is a plus, that's a backward travel. If it's a negative, that's a forward travel. So it's a negative, because for this guy, wave is going the left. Defining process. And PS, XT, psi, right, is the left to right. So it's in the same direction as positive x direction, which is T minus x. This is about it. In the defining process, if you do well, then just the rest of the things out of manipulation of information. So now, one more. When you solve for this weekend, maybe, you will be already. When you deal with water problem, this is water problems. Incident shock wave is there, and it will reflect, scatter there. You have one more wave, which transmits into past the plate and move into the water in the other side. So you have to define the one more functions. Velocity potential function. This is something like a PI. This is a scattering PS. You have to define the PT, transmitting. For the transmitting, how do you want to assume that? The transmitting XT, you can't write L again, right? Because it's taken. This is arbitrary function. So you cannot use the same. If you use the same by accident, the result, if you do the computation carefully, your answer is okay. But use some other, maybe now, not this one, maybe T, side T. Of course, side T is to the left, correct? To the left. So now, how can you say T plus or minus? Plus, right? Going negative, that's equal. And that's over. We have to make all the calculations, it will be fine. So here is PI, PS. Then again, use this three equation set plus this to this problem. For water-water situation, you have one more, right? That's what you have to solve. And once you define it like this, you don't have to worry about the outcome. Automatically tell you what the result is. So for in this case is Tx is scattering to be expressed using US, scattering through the particle velocity. So over here, all I did is this relationship. Do you know this relationship? Yes. P is equal to rho P dot right here. That's what I then just replace it. This is del over del T. Then this function is right. Scattering is right here. Scattering is to the right of this. Then you just do the partial differentiations here. This is 1, right? Differentiation with respect to time t. And this guy I call the psi r star. So from here we can tell psi r star is equal to PS divided by the rho naught. Then, by going back to definition 1, this is what you know. Then US, just plug into the definition of the psi s and do the calculation. Then you will have this relationship. We know psi s in the previous page. This. From here, psi r star is C naught times US. Then you plug in this expression into the bottom equation here. Then you will get, you can delete psi r, because psi r is the vehicle. That's not the function you want. Then you get the relation between PS and the US. That's what we have done. And next Monday, I'll do this very quickly and finish. And spherical wave is a little bit more difficult. It uses the Laplace transforms and a little bit on the approximation method and get down to a very interesting result called the DAA result, double asymptotic approximation result, which is really exact in the high frequency region and low frequency region. That's what we want to call implications of high detail, and the full math is in. So if you have a chance, I'll start here again. Next is surface pressure P, right on the surface of the solid. Okay.